can use logs to solve equations and simplify expressions. I'll just put up a couple of quick examples here. So first we have the equation e to the 0.01t equals 1000. The way we set that up, let's write it again, 0.01t equals 1000. What we want to do, keep in mind, the hard part of any equation is when the variable appears in the exponent, but that's what logs are for. They remove the variable from the exponent. So we're going to take the natural log of both sides. I'm choosing the natural log because the base in the problem is e. So just taking the natural log of both sides of the equation. Now, using the law of logarithms, recall that ln of x to the y is equal to y times ln of x. So using that rule, I can write 0.01t times ln of e equals ln of 1000. So now I can write 0.01t. Keep in mind that ln of e is just equal to 1. I don't want to mix up decimal points and multiplication signs, so I'll write it that way, equals ln of 1000. So now I can just move everything over to the right and get t equals ln of 1000 over 0.01, which this is like dividing by 100, so this is actually equal to 100 times ln of 1000. Okay, next we're going to solve the equation 2 ln x equals ln of 2x. There are actually a couple of different ways that you could do this, but I'm going to just show you one of them because it demonstrates a particular point. So the first thing I'm going to do is I'm going to change 2 ln x into ln x squared. Again, that's the same rule that we applied here, and we can do that. So this is going to be ln of x squared equals ln of 2x. So now what I want to do is I want to raise e to both sides of the equation. Anything I do on the left, I can do to the right. So just putting in an arrow for exponent like on your calculator. So e to the ln of x squared is equal to x squared, and e to the ln of 2x is equal to 2x. Now I can solve this. X squared minus 2x equals 0, giving me x minus 2 equals 0. So x equals 0 or 2. Now, the thing that you have to recognize here, and this is the reason I did this equation this way, even though there was probably an easier way to do it, is if you solve it this way, which is perfectly legitimate, you then have to go back and check that some of these solutions are not extraneous. The 0 actually is extraneous because there's no such thing as the natural log of 0. Natural log, or any logarithm, is only defined for values that are positive. There's no such thing as log of 0 or the log of a negative number. So the answer is actually just 2. Next, we're going to do some simplification. So to simplify, this is the log base 121 of 11. In order to do this, the easiest way to do it is to recognize that 11 is the square root of 121. So I can just write that that's equal to log 121 of the square root of 121. This is rather convenient because that gives me log 121 of 121 to the 1 half, which equals 1 half log 121 of 121. And log base anything of itself is equal to 1, because remember the question we're asking is, what do I have to raise 121 to the power of in order to get 121? Well, the answer is, we know of course that 121 to the 1 is equal to 121. So that gives us our logarithm. So this is just equal to 1 half times 1, which is 1 half. Next, we're going to simplify log base 2 of 48 minus log base 2 of 6. Now, if you'd plugged either of these into your calculator, you would see that they both come out to fairly ugly decimals. It's not like each of these is an integer, and yet we can still get an integer answer in this case just by using the rules that we know. This is going to be a straightforward application of the quotient rule for logs. So this is going to equal log base 2 of 48 over 6, which is log base 2 of 8, which is, you can do it this way, we can just say, actually it's easier to just recognize that 8 is 2 to the 3, so I'm just going to say that it's 3. What I was going to show you is that if you couldn't remember that, what you could have done is said, okay, log base 2 of 8 is equal to log base 2 of 2 to the 3, which equals 3 times log base 2 of 2. And then, there again, we see that rule that log base, log base anything of that base itself is going to be 1. So this would just be 3. So that would be the same way to solve that problem. And then finally we have something a little bit different. Log base a of 5 equals 2, and what we're really doing is solving for a. So what we're going to do is we're going to raise a to both sides of the equation. So a to the log base a of 5 equals a squared. So a to the log base a of 5 by definition is just going to equal 5, because remember, exponent and log are inverse functions of each other. So if I compose them, if I write a composition of them, I just get this value here. So 5 is equal to a squared, and then a is just equal to the square root of 5. Technically, by the way, this equation has two different solutions, positive root 5 and negative root 5, but for the same reason that the base of an exponential function is always a positive number, the base of a logarithm is also always a positive number. So we can exclude the negative solution.